Okay, I think we can get started with the morning session. We're going to hear some FMO physics today. And first talk is Renato Higa on effective field theory and FMO physics applied to dilute ultra-cold atoms.
Okay, thank you. Where's my presentation? All right, thank you. So first of all, let me thank the organizers for the opportunity to talk in this nice workshop, especially Mair Hussein and Vardelei Banhato. So I'm an outsider of this field, and actually I see that this workshop is highly concentrated on cold atoms, and that's the first time I come to a workshop like this. Usually I go to workshop that deals with interdisciplinary aspects of cold atoms, also with nuclear physics, which is my line of research. So this is my institution, University of São Paulo, and I belong to a group that is make research on hadron physics. So this is an acronym of Hadron Physics Theory Group. So my background is on hadron physics. I'm mostly interested in QCD and its interplay in nuclear physics. But I deal with effective theory, which is a tool that is also applicable to cold atoms. And I will try to speak the same language as possible. But I wanted to make this sort of connection. So when Mair asked me to talk about FMO physics, I was kind of cornered because I didn't know how to contribute to the workshop. And I decided to bring you a little bit of these interdisciplinary aspects of nuclear physics and cold atoms, and show you a little bit of universality and FMO physics, which is, it has its roots in nuclear physics. All right, so this is the outline of my talk. So first of all, I'll give an overview of cross-disciplinary ideas that is at the root of effective field theory. Then I'll talk about EFT with short-range interactions, and I will say a few applications of universality and these ideas in cold atoms. And then I'll talk a little bit specifically on a recent work that I've been working on, which is making a cluster EFT and trying to simplify the dynamics of atom dimer. And of course, I put atom dimer for you to understand, but actually this is a nuclear system, all right? And then I'm gonna decrease the dimer by the energy and going towards the unitary limit and draw some conclusions of that, all right? So first of all, so this is the main picture that I want you to keep from this talk, that as I said, in nuclear physics, we have to play with this several islands of resolution, and somehow the goal of EFT, effective field theory, is try to bridge all these islands of resolution. For instance, if you go to very large distance, you are talking about astrophysical scales dealing with stars and evolution of astrophysical objects, in particular neutron stars, which from the nuclear physics perspective is the largest nucleus that you can study. And then you try to link that with heavy nuclei, and in between there is cold atoms, all right? And we push forward this, lowering the resolution, then you are at a nuclear scale with even fewer and fewer nucleons. You go to light nuclei, and the path from heavy nuclei to light nuclei is full of mess, okay? So it's very hard and very complicated to describe those things, because heavy nuclei, you cannot apply statistics because there are not so many bodies, but it's not so few that you can apply more ab initio type of things. So then, once you go to light nuclei, perhaps you have the possibility to use more ab initio methods. And then you are faced with other challenges, which are the formation of exotic nuclei, which is similar to molecular dynamics in cold atoms. Once you go to very unbalanced number of neutrons and protons, you start seeing the formation of structure that looks like molecules. And that's the interplay that I usually like in this field, is the methods that you use to describe molecular dynamics is roughly the same for these exotic nuclei. And once you go lower in the resolution, you have to deal with protons and neutrons and ultimately try to link that with the underlying theory of strong interactions, which is quantum chromodynamics, or QCD, all right? One thing that I find interesting is that we saw in the first talk of yesterday, Vanderlei was talking about turbulence and thermodynamics of ultra-cold atoms. And there are a lot of relation with what we see here, which is the quark-gluon plasma. Quark-gluon plasma is a state that are supposedly built when you collide two heavy nuclei at very, very high energies. And it is believed, and there are several clues that this happens, that once you collide these very big ions, you form a very high density of energy, where supposedly quarks and gluons form a different kind of matter that looks similar to fermions, strongly interacting fermions. So that's the interplay with cold atoms, and there are even ideas of people trying to simulate quantum chromodynamics using cold atoms. So that's the message I wanted to give to you from this slide. And as I said, the basic idea is trying to not deal with the whole theory. So the whole theory for strong interactions is quantum chromodynamics, as I said. And the main idea of EFT is not to dealing with the underlying theory and try to describe everything from that. We try to be humble and try to choose just a specific energy regime where we can do calculations as rigorous as possible and try to avoid all the complications of an underlying theory. So the main things that we have to pick from EFT is trying to choose the best degrees of freedom that are relevant to your interest. For instance, if you are in this energy regime, which is very, very high for most of you, you have to deal with QCD itself. The degrees of freedom are quarks and gluons, and you have to try to build them to make nucleons, protons and neutrons and nuclei. Once you go lower in energy, there is a complication on QCD that the dynamics are so involved that you cannot solve that. There is the hope that lattice QCD can give you some clue of what's going on, and essentially lattice QCD is putting the underlying theory on a supercomputer. And at the moment, you are only able to describe some static properties like masses and binding systems. So trying to get the underlying theory down to this energy regime is a big mess. So you better choose the appropriate degrees of freedom and try to make an EFT out of that. And that's what we do here, which I'm not going to go too much details, but we incorporate the symmetries of QCD on this effective theory, and this level of resolution is called chiral effective field theory, which borrows the symmetries of QCD and try to make the most general theory where you can organize the calculation of the observables in terms of a hierarchy. Usually you choose two scales, one that is a soft scale and one that is a hard scale. So that's also something that is at the heart of EFT. You have to pick up a hard scale and soft scale. And probably it's going to be clear when I discuss more EFT for cold atoms. All right? And the same idea goes down to much lower energy nuclear physics, where now the degrees of freedom are not neutrons and protons, but are nuclei themselves, right? And I've been working a lot on this field, but essentially the tools are the same that are used in cold atoms. So as I said, EFT is all about resolution scale, and as I said, a proper EFT only works if you have a very large separation of scales, so you have to identify at least two scales, one that is hard and one that is soft. And if you look at this cartoon, you have two objects interacting with themselves via an interaction potential, which might have a very complicated shape. And this is characterized by a length scale that I called R. So that R is the range of your interaction. But if you are probing your system with a wavelength that is much larger than this length scale, then you have a clear separation of scale, and that's how you can do business with this EFT. And that's the goal of EFT in cold atoms, is try to identify these two separate scales and work from that. And I'm going to show that this is at the heart of FMO physics. So essentially what we do with EFT, you try to lower the resolution until you simplify your theory. So suppose you have two objects that obviously are different, but these are two pictures at a very high resolution, and then you try to lower the resolution. You can lower the resolution and still identify the two objects. And there are specific EFTs for appropriated if you wanted to still identify these two objects, differentiate these two objects. But once you lower and lower the resolution, at some point, they look the same. And I think that's the heart of universality in cold atoms. And this is also at the heart of FMO physics, that once you lower enough your resolution, you lose the details of short distance, and then things start behaving in a more universal way. And that's the universality in few body systems. At lower resolution, objects interacting with short distance, they look the same. So this is similar like making an approximation of your atom as a spherical call. And once you have your spherical call with this resolution, you'll even lower the resolution, and that call becomes a point. All right? So that's the main message that you should keep in mind, that EFT is all about talking about point-like particles and make a consistent approximation taking this extension into account. All right? Where these ideas came from, and it came from more than half of a century ago with Beatty's effective range expansion. So historically, what he did, he looked at neutron-proton scattering, and he observed that whatever potential interaction that you use for protons and neutrons at very low energies, all these potentials, they give the same prediction for observables. And Beat essentially parameterized the neutron-proton scattering in terms of what he called effective range expansion. And that brings the universality of neutron-proton interactions. That doesn't matter your shape of your potential. At very low energies, these details that are short distance, they are washed out. And all of them fall in this very universal expression. Okay, people, for some reason, they forgot about that. Nuclear physicists, they try to make more and more sophisticated potentials, and they look about the details and forgot about the simplicity of those things. In the 90s came EFT trying to describe nuclear systems in terms of the underlying theory of QCD. And one of the main steps in this EFT was trying to bring back this idea of Beat, that nuclear interactions are very short distance, so at very low energies, the details of the potential should not care. And this was reformulated in terms of a Lagrangian, so it's a tool that you use in high energy particle physics. We just bring that to hadron physics. And once you write a Lagrangian that incorporates this kind of physics, contact interactions, you draw some Feynman diagrams, and then you end up with an expression for your scattering amplitude that incorporates all the physics in this Beats expression, right? So once you talk about universality in short distance interactions, contact interactions, you are talking about this kind of physics, all right? What is new with this EFT? The EFT brings a more modern perspective of how to regularize short distance interactions. And that's the tool that we use in high energy physics, which brings back the notion of renormalization. So now let me say a few things about universality, and still linked with the previous slides. Here I have my two scales that I wanted them to be very separate from each other. This is essentially the Compton wavelength that is roughly of the order of the scattering length, and that sets me my low energy scale. And the high energy scale is the inverse, is roughly the size of the interaction potential. For atomic systems, you define the van der Waals length. This is defined in terms of the coefficient of the van der Waals tail. All right, this is 6, and playing this with the coefficient of the van der Waals tail, you extract a length scale that sets you your short distance length scale. All right. And for a few atoms, you can see, in terms of the Bohr radius, which is roughly half of an angstrom, you see how this short distance scale compare with the scattering length. So I selected a few of them that have the shows this universal behavior that I'm going to talking about. Helium-4 is the most prominent candidate because this ratio is quite large. So if you see the van der Waals length is 14, a Bohr radius, while the scattering length is 200. So it's a large ratio. Once you divide the scattering length with this van der Waals length, you have a ratio of 14. So from the EFT perspective, you may assign this 14 with my perturbation parameter. So for cold atoms, in particular for helium-4, my expansion parameter is of the order of 1/14. So that's how you would look like that. It's even more dramatic for lithium-6 because in the triplet state you have more than 2,000 times the Bohr radius for the scattering length, while the van der Waals length is of the order of 60 Bohr radius. And that gives me a parameter, a ratio of the order of 40. So that means my EFT would work at the level of 1/40. So that's much more favor to apply EFT ideas in cold atoms rather than nuclear physics, where those ratios are of the order of 3 and 4 at best. All right? And that creates a very fertile line of research where EFT could contribute to this field. So I'm talking just about two-body interactions, and at the two-body level, what we see is that the largeness of the scattering length, especially if they are positive, gives us the idea that you are forming a very shallow dimer, and that's the whole physics of of universality, the shallower you have your dimer, the more close to unitarity you are. And this, from the EFT perspective, you are closer and closer to what is called the scaling limit at leading order. And once you work with the renormalization group details of your theory, you end up with a non-trivial fixed point where the fixed point is precisely a dimer at zero binding energy. So that's the scaling limit. And the scaling limit brings us very interesting properties like non-relativistic conformal invariance. But at the two-body level, it ends up here. The more interesting piece is when you go to the three-body system. So this is a more or less historical path line. Around the 2000, EFTists would apply these ideas to describe the triton, because the neutron and proton, they bind very weakly, forming the deuteron. And once you try to apply these ideas to describe the triton, you end up with universality in three-body systems, where you describe where you were facing with Thomas and Efimov effect. So the way you deal with three bodies in EFT, you formulate your Lagrangian, and after you try to compute your scattering amplitude, you end up with the so-called STM, Skorniakov-Termartirosian equations. And this kind of equation has a property that it doesn't have a unique solution. You are forced to put a cutoff in your integral equation, and your results essentially depend on this cutoff. What is this cutoff? This is a cutoff in moment to space, and that corresponds to short distance. So once you solve this equation, you are very sensitive to short distance. But your physics should not be. And what's going on? What's going on is what is called the Thomas and Efimov effect there. The Thomas collapse is precisely what I'm saying. Once you put this cutoff to infinity, which is like putting the distance to zero, your bound state's not, your ground state's not well defined. You move your short distance to zero, your ground state goes to minus infinity. So you don't have a spectrum bounded from below. That's the Thomas collapse. And the Efimov effect is a more bizarre thing, that your spectrum is very geometric. Like your ground state energy has a value, and your first excited state is the value of the ground state divided by a constant, which is roughly 500. The second Efimov level is the first divided by the same 500. And the third, and so on and so forth. So that's a geometric spectrum, and that's the Efimov effect. It's better visualized here. So this is a log plot. And this is a result of solving the STM equations. And in order to have a unique solution in the STM equations, you are forced to introduce a third parameter, which is essentially the three-body physics that you put in. And once you put the three-body information in your STM equation, you end up with something that is called limit cycle behavior of your three-body interaction. So your three-body interaction will depend on this cutoff, and the behavior with this cutoff is log periodic. All right? And once you renormalize your system, you end up with this geometric picture, which is the Efimov spectrum. Those effects might be better visualized if you work with hyperspherical coordinates. Once you do a adiabatic approximation and go to the lowest level, you end up with a potential that resembles the 1 over r squared. And 1 over r squared is very particular because it shows scaling behavior at the non-relativistic level. Whatever scale transformation that you do in your coordinates, you end up with the same theory. So it doesn't have any knowledge about energy scales. And that's the scale invariance, okay? But this scale invariance is broken by the information that you are forced to put, which is the three-body interaction or three-body information somehow. And that gives me an extra energy scale that sets the scale of your system. So that's a scale invariant solution. And this scale invariant solution only makes sense if you define roughly the phase. And the phase, once you fix the phase, you introduce an energy scale. And that's something that is called dimensional transmutation. And you see this also in quantum chromodynamics. Quantum chromodynamics at a classical level is a scale invariant theory. But nevertheless, once you solve quantum corrections, you are forced to introduce an energy scale. And that's what is called the dimensional transmutation. All right. So that was the Efimov effect, and this is a summary of what I just said. You have two separation of scales, and you have scaling limit at the two body, but at the three body you end up with this limit cycle renormalization type of thing, and that explains me the Thomas collapse and also the Efimov effect. So this was much studied in the 60s and 70s by nuclear physicists. But many of them, they look at that as a pathology, so like a theoretical pathology for a long time, until came the cold atom community and pushed this field forward because they were able to deal with the two-body interactions and push your system to the unitary limit. So this is the Efimov plot, and what I wanted to draw your attention is that the Efimov levels are here, and this is the unitary limit, where the scattering length goes to infinity. So this axis is the inverse of a two-body scattering length. Here is the unitary regime. Once you go on this side of this dotted line, you are at negative scattering length. And negative scattering length, you cannot form the dimer, but you can form the trimer. So this is, in nuclear physics, what we call the Borromean system. And here, with positive two-body scattering length, you are allowed to form a shallow dimer and also a trimer on this side. And this line is essentially the atom dimer threshold. So once you are here, your Efimov trimers, once you increase the positive scattering length, at some point your trimer breaks down into a dimer and an atom because you have you now have a higher energy. So your thresholds are changed. EFT and Efimov laws. So that was the history of EFT. So EFT then saw the opportunity of playing with cold atoms. So many people were working on trying to describe a unitarity regime in cold atoms. And this is a prediction of effective field theory. So essentially you describe the loss rate, you factorize the a to the fourth power, multiplied by a function, and this function is has a prediction, universal prediction from EFT, and this was confirmed a few months later. I think that was in 2008, if I'm not mistaken. In recombination length in cesium atoms, trapped cesium atoms. So you can see on the negative side of the scattering length, you see this bump. And this bump is essentially when the denominator of this expression just goes through zero. And this bump is in the loss rate. And physically what it means the formation of a trimer. And then once it forms a trimer, it goes down to the next energy level, and then they change this trimer energy into kinetic energy, and then your atoms are escaping the trap. And this was the first sign of Efimov physics. And then many came after that. So let me put into context, so just going back to nuclear physics. This kind of EFT predictions and limit cycles were also useful in nuclear physics, trying to describe some correlations between low energy observables. A correlation that you usually see in nuclear physics is what is called the Phillips line, where the binding energy of the trimer is correlated with the atom dimer scattering length. And this correlation was a mystery because in nuclear physics, people trying to make several potential models for the two-body interaction, but once you go to the three-body interaction, the predictions fall on a line. And that line is the Phillips line, and this was unexplained for a few decades until it was re-explained in terms of this Efimov physics. All right? The same correlation you see between three bodies and four bodies, like the energy of the four body with the energy of the three body. This in nuclear physics is called the Chon line. And several other correlations involving electromagnetic transitions were also established in nuclear physics and explained by this limit cycle behavior. Another interesting connection with nuclear physics and cold atoms is this picture here that I think is very interesting. This is the dependence on the neutron-proton scattering length, nucleon-nucleon scattering length, all right, the two-body scattering length, as a function of the quark mass, the masses of on the theory of underlying theory QCD. And these are data from putting QCD on a supercomputer. And this is a prediction from EFT on the behavior of this two-body scattering length as a function of the quark mass. And you can see that it has this funny behavior. And this funny behavior looks very much like what you see in Feshbach resonance. The behavior of scattering length goes to infinity once your magnetic field are resonating, so producing an infinite scattering length. And also you can see in optical lattice, optical Feshbach resonance also produces this kind of behavior. And if you compare these with the dependence of the nucleon-nucleon scattering length with pion mass, looks like the quark mass looks like a button, pretty much like the magnetic field in your cold atoms, and the quark masses on QCD on the strong interaction side. So this is just to say that those ideas are heavily applied in what is called halo EFT, where you can also see these structures in nuclear physics. But I show just what is called the evidence of Efimov physics on that, because you only see one peak, while the idea would be to follow two peaks in ultra-cold losses in order to identify the distance between the two peaks with the Efimov ratio. Remember that the Efimov ratio is this 500 that I showed you. And in a few observables, you see actually the square root of 500, which is roughly 27. And what you would expect if you would have the ability to measure the next Efimov level would be another peak here in the recombination length, which should be of the order of 27, all right? The ratio of these two peaks. But this is not seen. The most direct way of proving Efimov physics was done only recently in 2015 by looking at helium atoms, actually, all right? And people were speculating for a long time that there would be an Efimov physics on helium-4. But only in 2015 they were able to measure that. What they did what is called the Coulomb explosion, where once you form the trimers, you shoot a beam of laser, you strip out the electrons on the atoms, and then by Coulomb repulsion, the remaining are going to fall, are going to separate with each other by Coulomb repulsion, and then you detect them on a plane. So it's quite interesting experiment, and they saw the sign of the excited state, and that's in agreement with the Efimov plot. So that was a clear evidence of Efimov physics in cold atoms. And of course, helium atoms are not on the unitary regime, but it's very close, and that's the level that they measure, the first excited state. And then I go back to nuclear physics and I ask the question, so how can I probe Efimov physics in a system where I cannot tune the scattering length? So an alternative is trying to look at virtual states and its prints on observables. So that's something that is not a new idea. People have been speculating about virtual states. And recently we tried to look at these virtual states as an Efimov level. So what we did specifically in this work, essentially we make effective field theory for the dimer as a single entity. So we even lower the resolution that even a dimer now is a one particle. And we look at the atom dimer scattering and try to see what's going on. And so then the question that is probed, to what point the dimer might be considered a tight core, and under which circumstance? The first question is not really a question, is actually a matter of resolution. If you lower the resolution, for sure your dimer is going to look like a point. And that's the approximation that we do. And we built an effective field theory for this dimer as a single particle with the underlying theory of 3 atoms interacting with themselves. So that was the theoretical play that we did, and we took the neutron-deuteron as a physical system, but the ideas also apply for atoms. So first of all, a little background on that. If you look at neutron-deuteron scattering, or atom dimer if you wish, the behavior of the scattering amplitude is quite complicated. It's not as simple as what we see in the Beatty's effective range expansion. So this is a two-body interaction. When you have an atom dimer, your K cotangent delta is not as simple as that. And that's what we try to incorporate with this new EFT. We have to incorporate a more complicated functional form of K cotangent delta in terms of the energy. And we realized that we could do that. So then for atom dimer scattering, your K cotangent delta is not simply a power series, but it has this a little bit more involved analytic structure. And this analytic structure is related to the virtual state that I was talking about. This analytic structure implies the existence of a virtual state, and what we did in this work was to identify this virtual state with an excited Efimov level. So what we did, the idea was to obtain the atom dimer scattering phase shifts from an underlying theory of 3 atoms, and then we fit those couplings to our new EFT, and then we track the virtual state as soon as the dimer binding energy is decreasing. So decreasing the dimer binding energy is going to the unitary limit. So that's the game we played. First we could formulate an effective theory for atom dimer with a point-like dimer. This is just complications that I don't want to spare you from that. The nice thing is that the scattering amplitude looks like this. It has a a very distinct analytic structure. And we find that the S matrix has 3 poles. Now there is a detail that one is a very deep pole that goes outside the theory. So we don't care. Any bound states that are outside the effective theory, we don't care. There is the pole of the virtual state, the pole of the virtual state, and it has a norm that is negative because it's a virtual, it's not real. But once you go to the unitary limit, it goes from the unphysical sheet to the real sheet, and then the normalization becomes positive. And there is also a redundant pole that, for some reason, people also forgot about that, but we went to the literature and we uncovered this redundant pole, and as the name says, it's just redundant. We can get rid out of that. So we don't care about this pole, and but unfortunately it's there. So what we did we took numerically the the atom dimer phase shifts, the predictions of these EFT, and we fit the lower energy to our halo EFT. And we don't go much larger than 20% of the range. And once we fit only this small range, all of that is sort of a prediction of our cluster EFT. So it works remarkably well, and it's not a surprise because we have the correct analytic structure of our scattering amplitude built in. And that's what we did. And once you go towards the unitary limit, there is a pole here that I forgot to mention in this expression. There is a pole in this K cotangent delta due to this structure. Once you start decreasing your dimer binding energy, it goes from imaginary to real. And then sorry, this is the opposite, from real to imaginary, and this K naught. And then K naught square becomes negative, and you see a pole. And this pole in K cotangent delta is essentially a 0 in the scattering amplitude, and 0 in the scattering amplitude is essentially the Ransauer-Townsend effect. So once you lower your dimer binding energy, at some point you start seeing the 0 in the scattering length. So the 0 is at sub-threshold, at physical values of neutron-deuterium scattering, but once you lower the dimer, it goes to the physical sheet, and it appears as a 0 in the scattering amplitude. So it's a nice physics that is built in. I'm not going to discuss those phase shifts. Now I'm decreasing the dimer energy, and the poles follow this trajectory. So here are the norms of the poles, and these are the trajectory of the redundant pole. So you see that it has a negative norm, and it remains on this quadrant. It doesn't go away. But this is the pole trajectory of the virtual state, which is on the unphysical sheet. And once I go towards the unitarity limit, before I reach the unitarity limit, it goes to the physical sheet, and it becomes the first excited Efimov level. So this shows that indeed the virtual state that I identify in the physical regime, once I go to a physical regime close to the unitary limit, this virtual state goes to the first excited Efimov level, and it becomes physical there. So we saw some correlations that people also found in previous studies, like a correlation between the scattering length and the effective range. And this is the Efimov plot of what we did. So this is the trimer. There are 2 channels in the trimer, so we essentially have 2 scattering lengths. These are the results when you have then at the physical point, and once you do one of then to infinity. So you essentially don't see any, the difference is not visible in this plot. There are some tiny differences, but it's not visible here. And here is our excited state. That at the unitary limit is an Efimov level, but once you go outside in the real world, it goes to the virtual state. So with this theory, we uniquely defined the nature of this virtual state as an Efimov level. And now what we are trying to do is trying to see if there is any observables that are sensitive to this nature of this virtual state. So let me summarize. I think I'm on time. So I just show you, try to bring you the world of nuclear physics to cold atoms and the interplay also between particle physics of strong interactions with this QCD. And there are some ideas that we perhaps may benefit from this cross-feeding of different fields. And then I went more specific and tried to look at the atom dimer scattering. And the atom dimer scattering, according to our studies, it shows a virtual state. And this virtual state eventually goes to an Efimov level when you go close to the unitarity. And so we could verify some correlations that was looking in some old nuclear physics studies. And what we can say is that we can put this hypothesis in a more solid way, in a, well, the rigorous way that we can do with this EFT that goes level by level in a perturbation scheme. And this also addresses an interesting point that Marcelo Yamashita is here, and he had fights with Mazumdar, because Mazumdar was claiming that if you have a pair that forms a dimer, and you go towards the unitarity limit, they were claiming that they would go to a three-body resonance instead of a trimer. But what Yamashita and collaborators shows is that they don't go to a resonance, but instead they go to this virtual level. All right. And what we can do, what money we can take out of that with this formalism of making the dimer as a single particle, perhaps we can simplify things with more particles, perhaps simplifying a system of any bodies with n-1 body techniques. So thank you for your attention.
We have plenty of time for questions. Yeah. Oh,
right. Just a few comments about Mazumdar and collaborators. Because they calculate that an Efimov state goes to a virtual state when they do not have any two-body cut. This is not possible. This is mathematically impossible. So Deltuva just calculate again our paper, the same problem, and he just reproduced our results. So it's for me, it's there is no doubt about Mazumdar and collaborators. I think they just made a mistake.
Yes, thank you.
I have a technical question. Could you go back to this Ors-Seagrave effective range modification?
This one?
Yeah. So what puzzles me is this puts in a virtual state, you said, right? Mm-hmm. Which is, I think, the pole on the unphysical sheet of this term.
Yes.
But it looks to me like there's also a pole on the physical sheet. Isn't that imply a real resonance? That has two poles, right, in the K plane?
No, the pole is just here, and here is subthreshold. So the threshold is a little bit on the right side.
But K can equal plus or minus I K naught, right? Isn't one of those a physical pole resonance?
Oh, that's a good point. I never thought about that, but I think it's just it might not be a resonance. It might be because this pole is not a pole. It's just a pole in the k cotangent delta. So that turns out to be a zero in the scattering amplitude.
Okay, I don't follow the argument, right? K cotangent delta, the denominator of that is like the S matrix, right?
Yes.
And so it seems to me like that will also, let's see, what does that mean? That, look.
Yeah, a resonance would imply some combination of the unitarity term with this.
Oh, okay.
Real
So this would be a zero of the S matrix.
Yes, that would be a zero.
Not a pole. Okay, I see. Anything else? Jose, come on. You know FMO physics. There must be something you're dying to ask.
In EFT theories, how is to include like corrections to the range, that the fact that you actually have finite range interactions, right? Is that a straightforward or it's ambiguous? Oh, okay.
Wow.
So should I repeat my question? Yeah, the question was how you include effects of the finite range.
Yeah, there are people who did that. So it's I would say it's straightforward, but people, some of them include in one way, some other include the other way, which might not be.
It's not entirely consistent.
I mean, the consistency is that if you look at this diagrammatic expansion, so range corrections would go like an extra term on this diagram, but it involves already the leading order three-body amplitude. Mm-hmm. So you just do perturbation theory on effective range essentially, and it's reasonably straightforward. It's not technically challenging.
Okay, but was that tested or benchmarked with a calculation that has a finite range interaction?
In nuclear physics, they did. Yeah, in nuclear systems, they did that. But in nuclear physics, the complication is because people cannot say how large or how small are range corrections.
Okay.
And that's the controversy. The controversy is just that, because people claim that it's not small enough. People say that it's not large enough. In cold atoms, I don't think that will be a problem, because range corrections in principle will be much lower than the scattering length anyway.
Okay.
Following up on that, so for instance, the near universality of the three-body parameter in the presence of van der Waals forces, I don't think that's been derived from effective field theory, as far as I know.
No, yeah, and I think that's an issue, yeah.
So you haven't tried to do that yourself?
No. Perhaps we have to deal with the long-range van der Waals sort of with a two-body type of potential and try to make the EFT for the short range and leave the long range explicitly. I think Dean Lee have looked into that. I'm not mistaken, but...
Okay, I wasn't aware of that.
Okay.
Yeah, I was just wondering on this triton system if people have thought about how to, or if they've come up with ways to see the effect of the Epimov states.
Yeah, that's a big issue because the two-body it's shallow, but the trimer is not that shallow. And people argue that because the trimer is not that shallow, you're outside Epimov physics. One way to try to look at Epimov physics on that is precisely what I'm proposing, trying to look at the virtual state. because in the triton channel there is a virtual state. And what we showed in this study is that this virtual state, if you theoretically tune the two-body binding energy to 0, at some point that will become the FMOV excited state. So, no clue. Perhaps you have to look at the physical situation. So you have to see effects of the virtual state on scattering. So that's the only way you can try to. One thing that perhaps the ITA group is looking at the cross sections. At some point it goes to 0 because the zeros are related to the zeros in this in the amplitude are the poles in the K cotangent delta. So the pole in this expression are zeros in the scattering amplitude, and if you look at the cross section, you might see some zeros. So it's trying to look at the observables and try to connect that with virtual state effects.
I think to see the effect of virtual states, just if they are very close to the cutoff, to the two-body cut, then you have to make some experiment on scattering, try to look at the cross sections and so. And just another question: just what's the main conclusion of your paper you published in 2019? Because it's known long ago that an FMOV state comes from a virtual state. It emerges from the two-body cut. So I just would like to know what's the main conclusion of your.
Yeah, our initial thought was to do the cluster EFT for that, and that's what we did. And we see that it works because we do a cluster EFT making a dimer point-like. And it agrees with the theory with three bodies, so that's the main thing, and we just look at this virtual state as a playground. So, but I agree, people have been derived, but not in an EFT context. So it's just a model, and we try to eliminate model dependence on that.
I don't know. I ask you for your opinion. Together with the people at the San Jose dos Campos, Federico and others, we're trying to incorporate the FMOV effect in a couple channel description of reactions. And basically you have 1 over rho square effective potential that comes from these from the FMOV effect. Yeah. And it looks to me that like you're exciting a monopole state, large monopole. In fact, basically what you have is an excitation of a monopole state, which has an excitation energy very close to 0. I mean, it's very small excitation energy. Mm-hmm. Do you have any comment about this? I mean, you know, this is.
Yeah, I think you told me once that idea. I honestly didn't think enough, but I think it's compatible with what we have, having this monopole idea of.
Yeah.
Whatever.
Okay, yeah. So we will continue.
Yeah, sure.
You agree?
Uh-huh.
You agree that we should continue our work?
Sure, absolutely.
So by monopole, are you talking about like a hyperradial breathing mode? I think that's what. Mm-hmm. I think that's close to our description in hyperspherical coordinates as well. Yeah. Okay, it looks like there's no more questions, so we can have coffee and be back at 11:20. Okay, I think we are ready to resume. Jose Dincao from GILA and the Department of Physics at the University of Colorado will tell us about his few body stuff, non-equilibrium dynamics.
Okay, thanks, Chris. First of all, I want to thank the organizers, Mahir and Vanderlei, for giving me the opportunity to be talking to you, right, about some of my latest studies. Right? And maybe I should warn already from the start that this talk is not exactly how I thought it should be when I first wrote the abstract. And essentially because the non-equilibrium aspect of this talk turned out to be a very interesting problem. There's a lot of parameters, the parameter space is huge, so I don't have a fully coherent story, but I do want to show some of what we have seen because I think it's very interesting. So this talk is also include 3 experimental projects that I have been involved that I believe that is teaching us a little bit how to build up field body models to accurately describe collisions in ultra-cold gases. So yeah, anyway, most of my work comes from this interplay between 2 different fields, essentially. The ultra-cold gases, where people are normally concerned about the collective behavior of the system, and field body systems, which is a more microscopic view of what is going on inside these systems. Right? And apparently it doesn't work with Mac, that monitor, right? Yeah. Maybe you can sit over here? Yeah. Okay. All right. I have a mechanical laser here. I need to coordinate. So, okay, what are the characteristics of these ultra-cold gases, right? I like to point out that those are clean and accurate experimental platform. You can really control what's going on in there, right? To produce, you can apply magnetic fields and electric fields because the temperatures are very low, so the effects of these fields are very efficient, right? Which would not be in a thermal gas, right, at temperatures. But they also have the ability to control the quantum states. You can create a system where all the atoms are in exactly the same quantum state, and that's very important if you want to see coherence and you want to do precision measurements. They also have the ability of control the interaction, which I think is unique in many of these, in different research fields. Using, in that case, special bioresonance, which I think most of you guys are familiar with. And encompass different research fields, right? It's almost an interdisciplinary field these days. There are a lot of nuclear physics and, of course, atomic, molecular, and optical physics there too. Right? On the other hand, field body systems, right? It provides a variety of quantum states, right? We know we have the FMOB states, we have Rydberg molecule, halos states, and different kinds of dipolar states. We never named those states, but I guess at some point we should. But there's a whole complexity there. And it also has a strong theoretical foundation. We have methods that can provide insights, like a hyperspherical method, quantum Monte Carlo, effective field theory, and it's important to be able to describe the system precisely in order to make advances on the experimental side. And of course, there are opportunities to create more exotic phases based only on the field body physics, right? Here, I'm just showing some nice pictures to distract you guys, but those are real research going on. And in the context of ultra-cold gases, it is inevitable that you are going to see field body physics there because the field body physics, in that case, it is responsible for atomic losses. Right? Whether or not you want to dig into field body physics, experiments will always suffer from some form three-body losses. Right? So these two fields, I think they are complementary, right? And they are building up what I like to think like a new research venue, right? Where you can explore new effects. And that has been a very active field, really. But why do we care about it? I think I already say, at least in the context of the ultra-cold gases, the problem is the stability in lifetime. Right? That was observed since the early experiments in Bose-Einstein condensates, three-body losses, in which, well, three-body recombination is the one responsible for such instability. Right? And that's a process where three atoms collide to form a molecule in a free atom with enough kinetic energy to escape the trap. Well, actually, if the released kinetic energy it is larger than your trapping potential, that's an actual loss. You're going to have a reduced atom number. Otherwise, if it remains trapped, it's going to cause heating, and heating is the coherence, and you don't want that. And things get worse if you consider the scaling on the recombination rate, K3, with the scatter length. It goes to like 8 to the 4th. So close to a Feshbach resonance, where the A is very large, this term becomes dominant. So your system becomes highly unstable. And there are many other processes, few-body processes in a gas that can lead to losses. So it's important to have a control, and know what's going on in all that. And in a way, the theory has a good handle on that. We know that for most of the processes, what is going to be the scatter independence. I don't want to get into detail of this table. This is just to show you that we can list how these losses are going to behave. And that is allowed, it's possible in the end of the day because we have the FMO physics, like Renato was talking previously. The FMO physics allow us to derive this scaling loss. So it's a very important phenomenon in field body physics. Now, of course, this is just observation that we understand the losses, but we still don't know how to control them. And I think that's the next frontier, which is learn how to really, in some cases, reduces the losses. In other cases, you might even want to increase the losses. But that's still yet to come. Now, I thought that I should perhaps give a little idea of how we think the field body problems. In my case, using the hyperspherical representation, you can look at a Hamiltonian for a field particle system, just given by the kinetic energy and the interatomic potential. In this case, if you write in spherical coordinates, you're going to have a set of coordinates, a number of distances and angles. The hyperspherical way, you transform the Hamiltonian in terms of a single length scale, which is the hyperradius that gives the overall size of the system, and all other degrees of freedom are going to be in angles. And these angles are what describe the internal motion. And this equation is very general. It's valid for any number of particles. You always reduce to a single length, and the remaining degrees of freedom goes to angles, the hyperangles. And the ones that we like to use are what we call... Okay, thank you. Close enough. Now I can hear myself. Okay. I apologize. Okay. The internet's complaining. Uh-oh. I'm in trouble with the internet now. Probably, yeah. I'll put it in. Okay, anyway, there is a whole business strictness here, right, of which hyperangles you're going to use, right? It's not, there's some hyperangles that are more appropriated to some kind of problems than others. This one in particular, the one that we normally use, the Democrat hyperangles, that's not a political statement, but it's democratic because it's going to describe all particles in the same, I don't know exactly why they call it democratic, because I guess describe all partitions equally. Right. But anyway, it makes the fragmentation thresholds, the hyperspherical make the fragmentation thresholds very clear. The symmetrization is simple in these hyperspherical coordinates. And essentially what we do is to write the wave function, right, and using this quasi-separability of this Hamiltonian. Right. You see the hyperradial dependence only depends on, it's in here. So you assume that your wave function can be separated like that, and you solve the hyperangular Hamiltonian, which is the part that contains all the hyperangular degrees of freedom for fixed values of the scattering length, of the hyperradius. Right? And that's very similar to what you do with Bohr-Oppenheimer. And by doing that, you diagonalize this, obtain the eigenvalues, which are the hyperspherical potentials, and the channel functions, which are the eigenchannels, the eigenstates of this Hamiltonian. And once you do that, for each value of a hyperradius, you obtain a set of potentials like that. Right? And they have a physical interpretation. You can look to them and know what they are telling you. Like states that belongs to negative energy here, in this case. I'm setting the zero like the energy of the three free particles. The channels that are below are channels that describe collisions between a dimer and an atom. Right? The states that are positive energy at large distances are the states that are describing, oh, okay. Yeah, it's appearing there. Oh, there we go. There it is, underneath. So it gives you a physical picture. For instance, states that are bound in these guys, in these potentials here, they are resonant states because they can break into a dimer in an atom. But states that are under this threshold, which is the lowest two-body breakup, right, are actual bound states. So, of course, to get observables, we have to solve the hyperradial Schrodinger equation, right, which is no different than other the two-body radial equation. Right. For instance, this is a multi-channel system, and I have considered coupling between all these channels. Well, those are here just a few numbers, right, that characterize the length scales that we do scattering and calculate energy spectrum for ultra-cold atoms, right? And that takes me to the one of the things that I want to tell you, right? Which are these three developments, three experiments that I believe are teaching us a few things, right? First, what I want to say, right, is more or less the status, right, in the way that I see the status of field body physics in this field, right? We have many models that use contact interactions, right, and that's great. Like EFT, they give you insights of the universal properties of the system, right? But there is still a lot of things that comes out of the physics by just studying, including the effect of the finite range interactions. Right? It taught us, right? It helped us to understand a new kind of universality in the system. Right? Like based on contact interactions, it was always taught, for instance, that the FMOV parameter, in this case, the position where the first FMOV resonance occurs, would be it would vary from system to system. Right? And experimentally, that was shown that that's not necessarily true. Right? In this picture here, I'm showing this is a collection of data. for different atomic species and different groups, that shows that the position of the FMOV resonance belongs within a range, right, with 15% of this number, approximately minus 10 times the van der Waals length. So this kind of universality was unexpected, right, and that's strongly connected with the long-range behavior of the interatomic distance. Right? So at this point, I think the field body physics started taking a more solid step in the direction of being able to predict what you should see experimentally, and at least within this margin, right? I show different models with finite range interactions. They all belong to the same variation. Right? They give the same variation for the three-body parameter. So that was a point where the theory started becoming more solid in the sense that it can provide you some predictions. Right? And of course, afterwards, more experiments came. Right? And in particular, here I'm repeating some of the data on the left side, on this side, but there are new data here with potassium-39, right, that shows a deviation from what this universal prediction has taught us. Right? And of course, in this axis here, well, I didn't explain, in this axis is just the number of bound states that the model can support. So you see a weak dependence on the number of bound states for this particular parameter. Now on this plot, this is SRES, is basically is what tells you the strength of your Feshbach resonance. Right? If SRES is very large, that means you have a very broad Feshbach resonance. If SRES is small, you have a very small and very narrow Feshbach resonance. Right? And there are theories that predict a strong dependence on on this three-body parameter A minus on SRES, right? But the theory predicts a much stronger dependence than what is seen experimentally. So there are things that are not understood, right? And our question is, can we do better? Can we understand what is causing these variations, even at the finer level, to understand why one atomic species has this value, the other has the other one? You want to ultimately have a much better control of what's going on. Right? And this set of 3 experiments that I'm just going to talk about, I think it is telling us, is pointing us what is the minimum model for you to get that level of accuracy. Right? In this particular experiment, with I'm not sure if you can read here, is the group of Johannes Denschlag. They were looking to three-body recombination. The three-body recombination, as I said to you, right? This is a more realistic picture of how the three-body potentials look like. Right? And essentially, you have the 3 atoms coming together. Oops. Coming together, and then going over in a last transition and produce many possible final states. Because these two-body interactions support many two-body states. Right? And what this experiment has, which is unique, is the capability of detecting the final products of that collision process, of this chemical reaction, if you wish. And how they do that, this is just a schematic representation. I picked it, of course, they started with a sample of atoms, in this case rubidium-87, and I'm just singling out 3 of them. And they let it collide, right? And when they form the final product, they would fly apart because they release kinetic energy. But at that point, they ionize the molecule. And when you ionize the molecule, it's much easier to trap an ion than a neutral particle. So the molecular ion stay trapped, and they can count that how many of a particular kind of molecular ion they have produced. That's a unique experimental capability. And based on that, they were able to calculate something that for me, it was always in my calculations, but the hope of that being ever observable was very low. So we never look closely to what was going on with the distribution of final states. But these guys can actually go and measure that, right? One thing that they found, well, here in this figure, the circles are the experimental data. The theory is the crosses, the pluses. And on this axis, you have the binding energy of your molecular state. Right? So for the most weakly bound two-body state for rubidium-87, right, which maybe for 100 megahertz or so, right, is where most of the recombination goes. When your three atoms collide, you're going to populate most of this diatomic state, which turn out to be a S-wave state, S-wave dimer. But afterwards, you can see the numbers here are the partial wave for each one of these molecular states. And the first thing that was noticed is that there is a general propensity rule. How these states are going to be populated depends on how deeply bound they are. Right? It depends on this way. Right? It depends on the inverse of the square root of the binding energy. Right? You can get that from Frank Condon overlap and stuff. Of course, there's a lot of noise here, and those are likely to be interference effects when you recombine. And in theory, it's doing a pretty good job in first capturing this overall trend. At some points here are not coinciding. So it's still a rough agreement. Right? You can see this point here is perfectly good, right? But because there is a rescaling in the theory to match this first recombination fraction. So it's still a rough agreement, but the theory can give you the general trend and understand this propensity rule. Right? And above all, what I thought more interesting is that the value of a recombination does not depend on the number of bound states at some point. Because more bound states, you are just populating states that are down here. And in the population, and the chance to recombine to the very deeply bound doesn't matter much. So truncate the number of bound states in your model, it's okay. That's one lesson that come out from this study. It's a lesson that we could learn because we have experiment supporting it. It gives us a support that the theory can properly describe these decay channels. The next experiment is one there in Gila with Juni, right, where now they have this capability of stacking up atoms in an optical lattice site. Right? They can create optical lattice with one atom per lattice site. Right? And now we know that one atom is blue, and two atoms are green, and three atoms are red. Just kidding. But they can systematically include the number of of atoms in your lattice site. And in this particular case, what they were looking for is the signs of what they are calling multi-body interactions, right, which are anything that deviates from the sum of the pairwise interaction. But they, can control the quantum states of these three particles, and they do by starting the system with atoms in a ground state and exciting one of them to, in the case of three particles, to these two possible states, EGG, G and E, sort of ground and excited states. And in this case, it has a minus symmetry because it is, if I'm not wrong, it's antisymmetric in space. This is strontium-87, which is a fermionic atom, right? So the total wave function has to be antisymmetric. So in this case, the spatial part, it is symmetric, but the spin part is antisymmetric. And in the EGG plus, it's a case of mixed symmetry state, but the total wave function is still antisymmetric. Oh, I'm pretty late. In any case, the key thing in the hyperspherical representation is to describe these collision processes. Well, it's really not a collision process because you have the trap that keep the atoms together. But still, they can decay to some other molecular states. Right? And that's how I do this calculation. I calculate this energy, which is a resonance, and calculate the width. And calculating the width, I extract the lifetime of these states. And you can see a very good agreement between the theory and experiment, especially for the GGG state, right, which are ground state. The theory are the open circles. And for the EGG minus, it's a very good agreement too. And for EGG plus, which is a state of mixed symmetry, the three-body model fails because it does require a multi-channel description of this particular state. So we understand this case that doesn't work very well. It's still good enough. But again, this calculation does not depend on the number of molecular states your model has. Okay? The third experiment, right, so just to emphasize here, this is a more quantitative agreement than previously. In the case of rubidium-87 recombination, it was a rough. There is a factor 2 basically between what the result we see and what the experiments see. In this case, the results are within 15% or less for the three-body lifetimes. So we start speculating possibilities, and even experiments are not consistent with themselves in the case of rubidium-87. What one experiment obtains for recombination in rubidium-87 is different than the other one. So there is some controversy there. Now, in this case, this is a more FMOV-like experiment. It's a new experiment that is running there at GILA. Right? We are about to submit this manuscript, and I'm just going to show some of this data, right, which is for potassium-39. Again, potassium-39 was one of the cases in which the value of the three-body resonance, A minus, right, the three-body parameter, was deviating from what the universality would give. So that's an interesting case to study. In this case, I'm showing here the measured three-body recombination rate, where you can see a very good fitting with theory. This theory is a finite range. Sorry, it's a zero-range theory with finite temperatures, at finite temperatures, and it fits very well. But this theory cannot predict what is eta, which is this inelasticity parameter. That's a free parameter in the theory, and actually A minus is also a free parameter in the theory. Right. So in this case again, right, this is the value of A minus they obtain, right, negative 14, which is 40% different than what the universal result is going to be. And the value of eta, which is this inelasticity parameter, is 0.25. It is extremely large in comparison to other atomic species. And in this scenario, right, what they were able to do is to get these 2 points here are exactly the same states. Right? They were able to narrow this error bar and put a much better bound to the value of the three-body parameter for potassium-39. And what I wanted, right, in this project was really to have a model that can incorporate the hyperfine structure of potassium-39. Right. I don't want to go much in details of this, but we know atoms in the presence of a magnetic field are going to feel the Zeeman effect. You see that you can tune the hyperfine interactions. On the two-body level, things you want to have a three-body model that has the proper molecular structure. In this picture here is kind of what I did. I put these two particles in a harmonic trap such that the continuous states are discretized. So I can see the actual molecular states are over here. Those are the Feshbach resonance. This is the Feshbach resonance that the experiments deal with. And you can see that these states continues when they go to continuum state. So it's a nice way to plot. Those are the hyperfine quantum numbers. The black solid lines are the hyperfine energy levels. It has a function of the magnetic field. And for a case like that, the interaction is given by this way. It's a combination of a singlet and triplet interactions. And these singlet and triplet potentials, they are very complicated. They are very deep molecular states. And they support too many molecular states, and the calculations would be extremely challenging. So what I do is to model the singlet and triplet interactions in terms of a van der Waals, Lennard-Jones interaction, where this parameter, lambda 0 and lambda 1, is what I tune to produce, so this model gives me the right singlet and triplet scatter length. And, well, there's a few more approximations, but I think that's all under control. And I can use this model to obtain three-body potentials and do three-body calculations. As realistically as possible, I would say, so far. And what I have seen in this calculation, here I'm showing my values of A minus. It has a function of the number of singlet bound states. The triplets are always one more than that. Singlet S-wave bound states. So when I have just two S-wave states, my three-body parameter is close to -8. But as I increase, this shows a strong dependence on the number of bound states. It does approach the experiment, but this strong dependence, it is very different to what we have seen for broad resonances, which are the black solid, the black points here. There, the three-body parameter does not depend very much on the number of bound states. But for a narrow resonance, it seems like there is a strong dependence on the number of bound states. And what I thought to be interesting, too, is that my calculated value for eta, it does approach the value that you see experimentally. I mean, of course, that for a small number of bound states, it's off, but approaches the experiment over here. And there is also this behavior even for broad resonance. Eta seems to converge as a function of the number of bound state. But the fact that we can is the first time that I think is the first time where theory can actually predict this eta parameter, which is related with the lifetime of the state, is related with the recombination rate, and so on. So I thought the lesson here is that, first we see a quantitative agreement with the experimental data, and we learn that it's important to have the proper interaction model in order to get more quantitative predictions. I have to have the singlet and triplet interactions that has the right bound state structure to get realistic results. Okay? All right. I think the message of that first part, describing these three experiments, was really to say that there is a push in trying to make the field body theory to become more and more quantitative, right? Where you look to the fine changes of your system and understand what is causing the variations on the three-body parameter. Now, this second part, which is the part that originally planned, right? It's kind of benefiting from that, right? Because now I know that some of what I found is going to be experimentally consistent in the sense of lifetimes and so on. And the question behind this exploration is a big question, right? How an isolated quantum system reaches equilibrium. Right? We know that classical systems in mechanical statistics describe well the irreversible aspect of thermodynamics, but it cannot describe we know that quantum systems, a finite quantum system should be, in principle, a priori, be reversible, right, in time. It was really with when the eigenstate thermalization hypothesis come up, is that you could reconcile what most people see in laboratories, that finite quantum systems do thermalize, they do equilibrate, right? And that's it's open up ways to explore this subject, right? And one key, those are the first few works on the eigenstate thermalization hypothesis, and a key ingredient in all this is chaos. Right? Your system have to have chaos. Right? Of course, that by itself is a huge topic. What is quantum chaos? But we can come. There are some hypotheses that says if your classical analog, classical analog of your system is chaotic, the quantum analog system should be chaotic too. All right. But my question here, when I was looking to these theories and so on, I thought, well, can I apply ETH or explore a few-body system under the perspective of ETH? Right? I mean, they are. Right? We know that three-body classical problem, it is chaotic. So the quantum analog also should have some hints of chaoticity there. And I mean, the classical system is chaotic. The quantum system, yeah.
Remember that in big debate in the 90s about quantum chaos, there is these levels of statistics and stuff like that. So what do you mean when you say the quantum system is chaotic?
Well, I didn't mean to say that because I don't know what a quantum system, what is the chaoticity, how to define the chaoticity in a quantum system. Yeah. Exactly. Yeah. In the way that I looked to that, I looked some energy spectrum and I see if it follows a Poisson or a Wigner-Dyson distribution. Okay. But I don't want to get into this discussion because in the end of the day, I can calculate the observables and see what I get, and see whether or not the hypotheses coming out of this theory are true. All right. But and that's the question here too, right? Does a few particle system requires fulfill all requirements to see equilibration, right? Ultimately, I can spend a lot of time trying to answer those questions, or just go straight and do a calculation, right? And that's what I did, right? To see if there's water in the pool. But of course, I looked to the three-body potentials, right, and tried at first characterize chaos there. In my case, I am actually inspired by this work where they did this kind of analysis, which is get for a given hyperradius, you have an energy spectrum. Okay? And looking into this energy spectrum, I determine whether it's a Poisson or Wigner-Dyson. Right? And of course, the Brody distribution, which is a mixture of Poisson and Wigner-Dyson, it's going to work better in this case because it can tell you the degree of chaoticity, if you wish. Right? But in terms of the hyperradius, you find that when Q is equals 1 or close to 1, you have a Wigner-Dyson, so presumably some chaos. Right? And as the hyperradius increase, you see less of that. So the particles are getting far away, right? And of course, this characterizing chaos, it is complicated in this system. In reality, I don't think the Brody distribution is a good distribution to describe this energy spectrum, because at large distance, you get a Poisson distribution. You really get is a mixture of a chaotic spectrum with a regular spectrum. That's it is a body. So I have to come up with a new way to do that, and that's an ongoing thing. But there's good hints of chaoticity in the problem. And for me, that was enough.
It's after all, the Brody distribution is a periodization that takes you from one limit to the
To
other.
the other, yeah.
We have something better than that,
Okay.
based on the maximum entropy principle, and it's we call it the deformed Gaussian orthogonal ensemble.
Okay,
We
the
deformed
Gauss
the
orthogonal
ensemble.
is
So I could show you that.
Sure. Yeah, I'm looking for ways to explore better this energy spectrum because the Brody distribution is not functioning very well. It functions well when it is almost a Wigner-Dyson, but as soon as you start deviating from Wigner-Dyson, it does not go to a Poisson distribution. So that's being kind of exploratory by using the Brody distribution. All right. So, but all that, this hint of chaos in the three-body interactions, in three-body potentials, for me, was enough to propose a way to see equilibration or the non-equilibrium dynamics in the system. All right. My idea is you start with three particles in a harmonic trap and quench this trap. You make a very weak trap in the beginning, and your final trap is a very tight trap. All right, I'm doing in the spectrum of the three particles in a trap. It is here. I'm just showing the low-lying states. There are way more states here that are populated that are not shown, but it's a complex energy spectrum. Right. And well, everything here comes out naturally from this sudden quench approximation, right? After you quench, your wave function is going to be a superposition of the eigenstate of your final Hamiltonian. There is a time-dependent phase here, and of course, there's C beta, which is this is going to give you the population of your system in that particular state, right? Coming out of a psi zero. Right, which is our initial state here, okay? And which observable we're going to be looking? Well, I decided to look to the average size of the system, right? So for that, I calculate this expectation value, right, which is the sum of the three interparticle distance divided by 3 by normalization. And you can write down, you just expand these expressions and obtain something like that, and then you can see explicitly the time dependent in this observable. Okay, and if ETF applies to this system, what you should see at long times is that this guy converges to this number. All right, all this time dependence is going to go away, and you only have the first term of this expression. And that's more or less what we have seen. All right. When I calculate, this is a calculation where my initial trap, the ratio between the oscillator length in my initial trap and final trap is about 4. So I squeeze the atoms a factor 4. And the scatter length is about 10 times the van der Waals length. Right. And it has a function of time in units of the trap period. Right. You see in the beginning, after a few trap periods, you see the system oscillating, but at some point, it converges. The amplitude of these oscillations are reduced, so the system is equilibrating. Right? And I do that for different values of the final trap, right? But always the same ratio. Okay, and you see that there is some non-trivial dependence. Well, I'm going to talk about this later. Okay. Then the next thing that I did was to look the distribution. 5 minutes? Okay. The state distribution seems to follow a thermal distribution for the higher energy states. Okay. And it always gives, if you have a thermal distribution, you can extract some temperature from this results, which it turns out to be always the same. Right? So it depends mostly on the quench. Right? Well, there's still lots of things to understand. Right? There's non-trivial dependence on the time, damping time. Right? When here the beginning was after 100 periods, but then it went later, and then now it's it's back to shorter times. So there's a lot of factors we have to look at. For you to have idea, right, if I'm looking to the damping factor, which is the ratio of your initial amplitude of oscillation and the amplitude of your final oscillation, is how much the system has damped. It depends strongly on your trap the trap of the oscillator length of your final trap, right? And there's some non-trivial dependence there, right? And that's likely because of the non-trivial aspect of the energy spectrum. Like for each point here, I'm here just zooming in this region, and you can see a lot of avoid crossings, and you can have. We're going to have to trace it back and be able to describe, to understand it, because we should be able to understand all this behavior. Those are not noise. Those are badly resolved fine structures. Right. And of course, there are cases in which we don't understand exactly the time evolution. You see, at this point, the system was oscillating and then suddenly increased, and then reach some sort of equilibration over here. So there's lots of things we don't understand yet that is going to require more and more analysis. And I guess with that, I'm going to leave you guys with some of the points that I hope I came across in this talk. I also thanks some of my collaborators. Okay, thank you very much.
In this last example that you gave, so the off-diagonal elements, they all die out in this under these circumstances?
For the matrix element?
Yes.
Yes. Yeah.
So they all go to zero. And then how does that depend on the quench? So the final temperature, if you assign a temperature, how does that depend on the quench?
The stronger the quench is, the higher the temperature, the final temperature.
Yeah, but in which way? So can you quantify that?
I don't. I mean, I have done a few cases and start tracking the temperature, but I'm not sure how is the dependence of the quench strength yet. We can, and I'm not sure if that's going to be, because there are some cases in which, oops, what's going on? Anyway, in some cases when you look, the population is not terrible. There are cases in which it's much more massive. That's what I was wondering.
And then if you can also extract some quantities like information entropy or
exactly.
Did you do this or Fisher entropy?
Sure. Yeah. No, we have done that. That's another parameter that we are looking at. But it's still because it is not a trivial energy spectrum. You see a lot of so we picked one parameter, which is the damping factor, to start focusing and trying to understand what is causing all these structures in our calculations. Then once we learn that, we are going to look to other properties of the system too.
Yeah, hi. I just wanted to ask you about your calculation for potassium-39. So you showed how the ratio of the FMOF resonance to van der Waals length depended on the number of bound states in your model.
Yeah. Yes.
And so two questions. What makes potassium-39 special? You mentioned that it was narrow. Is it narrower than the other Feshbach resonances that were in the plot that you showed, the data plot?
Yeah, in this plot here, I think. Oh, okay, here, right?
That one.
That's potassium-39. It's an intermediate resonance, right? S-res is about 1 or 2, right? So it's not extremely narrow.
So what makes it special?
So that's what we are trying to understand, right? There are D-wave resonances nearby, right? I didn't show the energy D-wave energy spectrum. Right, that shows some weakly bound. Actually, most of the recombination for potassium-39 goes to a D-wave molecular state. right? And there is a weakly bound d-wave state too. So it can come down to a level like that. It can come for really the details of the interaction.
Okay.
So,
So the reason why your current calculation isn't the same as the one that you did with Chris a few years ago, 2012, I guess,
no.
is because that calculation used the model potential. It didn't have the D-wave potential nearby?
Yeah.
Okay.
Yeah. So, well, sometimes that model gives you a resonant state, right? And we do see changes on even the single channel model when that happens, right? But those are not real states. That doesn't mean that the system is going to have that resonance. Now that I'm using a singlet and triplet interaction, I can tell, oh, that resonance state is real.
I see. So is potassium-39 the only example where the ratio doesn't go to 10?
I have done simpler models with different SRS, but just a couple of these calculations, and shown that the narrower it is, the more sensitive to the number of bound states it is. So there's something there that I didn't know. I was expecting to be just like broad resonances that doesn't depend on the number of bound states.
With an SRes of 1 or 2, that's not a narrow resonance.
Exactly.
Not
yeah.
particularly
Yeah.
broad, but it's
Exactly.
certainly not narrow either.
Exactly. Yeah. But I did calculations
not
for
unusual.
narrower than that. Right.
I'd be really curious to see how this hyperradial barrier changes. Have you looked at that as you change the
No.
number of bound states?
No, I did not. But definitely we learned that, right? That's probably the physics behind that.
Probably avoided crossings in the potential curves.
Yeah.
But I think that's a great clue that the D wave is the dominant channel here.
Yeah.
Because usually the S wave is the usual
Yeah.
dominant channel. And
The D-wave partial recombination rate is 10 times larger than all the other ones. Of course, that is 10% of the total, because you have about 200 states there. Right? So,
I had one other comment on your last part of your talk about the ETH, which was you said at the start of that discussion that the three-body problem is known to be chaotic. But I think what's known to be chaotic is the three-body Coulomb problem. I don't think, I'm not aware that it's been proven that it's classically chaotic, the three-body problem with short-range forces.
it's not the deterministic chaos, like the dependence of the initial condition. That's what I
don't know.
meant.
Have you seen that proven for
I think
short-range
that-
forces?
Oh, no, for short range. In classical mechanics,
Right.
I know.
Oh, that's what I'm talking about. So it is proven in classical mechanics with
Yeah.
short-range forces?
No. No. Gravitational problem.
Yeah, the 1 over r squared
Yeah,
forces,
yeah.
that's the case I know of. So I think that complicates the analysis here because
It
you don't
does.
know if it's even classically chaotic.
Yes. And that's why, in a way, I try to focus on the observable. All right, so I realize there's a lot of big questions in between, but I want to see if the system is going to equilibrate in the end.
No, that's really interesting. And one other question came to mind about that is whether you've looked for any evidence of pre-thermalization,
Which is...
where it's sort of, you see quantities starting to follow like a universal track before the system has really thermalized, but, you know,
Yeah, I didn't look specifically to that.
I know Vetrick's work on this has gotten kind of popular recently.
Yeah, I didn't track that. I did see some very weird cases that the calibration goes away, for instance. It was calibrating, you change a little bit the parameter, and then it goes away.
Well, that's a really interesting study.
Yeah, regarding the ETH, that's very fascinating. I mean, it keeps coming up with new results, even single particle and a chaotic potential. Now many body, and this is the first time I see for three
three
body.
particle system.
The issue is that I mean it's always at the stage of it's always at the level of a hypothesis. People are trying to pin down a more sophisticated theory, but it depends very much on the spectrum, and the analysis sometimes depends on how many levels you have available. And this is something I'm not from the field. So, what is the size of your spectrum? And is typically the few lower levels they don't follow RMT, and so you have to discard them. So do you do that? How the analysis is done? Yeah.
Well, there are in principle infinity energy states.
But how many you compute? How many take into account?
I can, depending on the quench strength. If it is a very strong quench, I'm going to populate many, right? And that can be a couple thousand states.
Oh, okay. That's you are really on the safe side. Okay.
But sometimes it's less because the distribution, you populate a narrow energy band.
So if this is the quench is not strong enough, you keep populating only the lowest level. Is that
just the
and
few
then
low.
probably you see violations of this hypothesis.
Exactly. You don't see equilibration at all.
Oh, okay. Well, that's
if I
consistent.
go a very weak quench, the system remains. I populate 2 or 3 states tops if I do that.
Okay.
And there's never a phase cancellation.
Okay. Thank you. Yeah.
Thanks.
Is that a clear experimental characterization of an isolated quantum system reaching equilibrium?
Would you say your system is equilibrated, Randy? Your lithium gas, your BC.
That's a very open question.
Sure,
I don't know exactly how to answer that, I guess.
Well, I think experimentally, it's you guys see your isolated system to equilibrate. Yeah.
You try to measure single point functions, of course, First, you measure single point functions, but then you also want to look at correlation functions or Fisher entropies or functions that are. One big topic is dissipation fluctuation theorem, but how to access it is not trivial because every measurement that you do in a many-body system will influence the system. So this is a big topic. So
that's a very simple question. That's a simple question that presupposes that there is some phenomenon you are talking about. And I'm not clear about what the phenomenon is.
So one of the things you could try to measure...
Experimentally, I mean.
Yeah, experimentally what you would try to measure in this case, for example, you would try to figure out whether your second-order functions follow a thermal distribution, for example. That's a weak signature, yeah, that you could do. I'm going to show equilibration measurements, which I can show for spin glasses. I will show this in my talk, yeah.
How isolated are
this? Yeah, that's of course we have to test. So the time scales are limited. He showed a nice. He showed
Mine
time
is
scales.
very well
His
isolated.
time scales are very isolated. I don't think that you can study a system over 7 or 8 decades. That's what you showed. But you can. This is.
Please give 1 second.
I mean, if you don't think about experiments for a while, so you just do computation, there is a big surprise that in the microcanonical ensemble, and you follow the evolution, you equilibrate. And then you are perfectly isolated from the theoretical point of view. Now the issue is, can you do that in the lab? And that's the catch. And this is a big surprise, and it's, you know, like there is explanations, which is a debate and stuff like that. But this is one of the key issues.
A lot of open questions, I'd say, especially when it comes down to implementing this, realizing these studies.
So, I mean, did you actually compute the final temperature you would expect? I mean, the energy distribution you would expect from a Boltzmann distribution?
Well, if I looked at distribution of final states, it's well, I do it by feeding, Chris. It will come. I think the next slide has a big figure or something. Ta-da. Okay. Yes, here. Those are the results from the calculation. I went too far. And if I plot this in a log scale, you would see that there's a linear slope.
So it does fit a Boltzmann distribution,
yes,
you're saying?
And from that slope is how I track define a temperature. Of course, that these states here are not following a thermal distribution, but
it should. I'm trying to think. So your quench preserves some quantum numbers, like total angular momentum and so on, right?
Sure.
So
yeah.
wouldn't it fit some sort of constrained thermal distribution?
Okay, I see. Well,
that only includes some of the quantum states for that symmetry.
That's true. I mean, the rotation of the angular momentum is still preserved, but I.
Does this have a temperature? Do these distributions correspond to a temperature?
Yes.
Then I think that answers that question.
This one? Okay. If I didn't want to plot in a way that became clear because it would raise more questions, but the questions came anyway. All right. The whole thing, this is a family of states that follow this distribution. All right. And those are states associated with one particular hyperspherical channel. Now there's more structure here of other states, but they all asymptotically have the same slope.
This is not what I would confirm.
Oh, I feel like there's a hint. I'm not sure how to define temperature with 3 particles anyway.
You could write down the density matrix, and you could check whether the density matrix is given by a thermal distribution that you could do.
Okay.
And here, obviously, it does not.
In which way it does not?
Because, as you say, it depends on what kind of sub-ensemble you choose.
Say that again?
Somehow it seems to depend on which kind of sub-ensemble you choose. Or a sub-ensemble of states in your case.
Well, that's the general rule. There are cases in which that doesn't happen, right? But I think those are exceptions. Are cases where you single out one of the states.
Now the question is what you call the exception, what you call the rule, right?
Well, if I identify what is going on in that exceptional case, right? Like if my quench is taking my initial state to 90% of one of the possible final states, that's exception.
Spherical harmonics, an answer to the chairman observation that you have some quantum numbers that are preserved in the quench, or is something totally different? Because then you have to separate in this subsets, no? If you preserve some quantum numbers, they don't mix.
Exactly. Yeah, they are not coupled.
This is really okay. Thank you.
Right.
But it's not hyperspherical harmonics. Those quantum numbers are not good. Certainly total angular momentum parity presumably is
parity
also
angular momentum.
Any more? Lively discussion. Cool. Okay, let's thank Jose again.
Thanks, guys.